Welcome everybody to the second half of chapter 12, and in this session we're going to talk about 7-segment displays, and we're also going to talk about synchronous counters as opposed to the asynchronous counters that we looked at in the first part of chapter 12. So the first thing we're going to talk about, and we've kind of already used these before, but I'm going to go into a little bit more depth discussion here. And so we're all familiar with 7-segment displays. If you've watched any sports in your life, especially if you are, well, I suppose now that all of the scoreboards are digital, but it used to be we would have scoreboards with 7-segment displays, really big ones, especially if you went to like a football game or a basketball game, and every once in a while a segment would burn out, right? And so we really don't have those issues now because we don't use this type of technology. We really just use more or less a TV screen or a monitor screen, something where we're projecting the video as opposed to turning on individual segments to represent a number, which is what the 7-segment display is designed to do. So on your proto board, on your Altera board, you have either 4 of these if you have the DE10 Lite, or you have 2 of them if you have the DE1. And so you can write to these, you can have numbers count, you can use it as a scoreboard, you can use it for pretty much anything. And all it is just an arrangement of LEDs in such a way that we can produce different numbers and different letters. Now there are other variants of this where there's more than just 7 segments. There are ones where, if you're following my cursor here, where you see these segments A, B, C, D, E, F, and then the middle is G. That's the 7-segment standard. If you have more of them, you could have an 8-segment, a 9-segment, a 10-segment. Sometimes through the middle here, you'll see 2 slants so that you could do, like if you wanted the letter K, you could have this segment on and this segment on, and then this diagonal and this diagonal. So there are other types of these out there. It's just that the standard 7-segment display, which is used in counting all the time, there is no number system where you're going to count to K. So that you would probably have different expectations for your project if you needed something more than this. So the way we're going to use them is to display digits in some type of count, whether it's just a counter or whether it's in some application for your project for the semester. So anyway, in this particular one, now I'm saying, you could have the diagonals through here. You can also have decimal points. So the digit itself, there's 7 segments, but then there's also a right decimal point and a left decimal point that you could turn on. And so now you could start to have, I always use the example of, like in a basketball game, under 10 seconds, they show you tenths of a second on the scoreboard, because sometimes, if the ref calls, if he whistles a play dead at 0.7 seconds, you want that resolution up on the scoreboard because you want to know how much time you have, if you have time to throw the ball in, turn, and shoot before time expires. So having that extra tenth of a second on the scoreboard, that extra resolution, is beneficial. And so you would have to switch the way you were displaying your 7-segment displays to reflect that, now the ones or the tens is in a different position, and then I'm also showing tenths. And so that's what the decimal point will allow you to do. And it's not just tenths. I mean, it just depends on what the sport is. If it was racing, you might take it out to the thousandth, right? So if you're trying to qualify for a position, I know in F1 and IndyCar, they both take everything out to the thousandths position. And there are times when, it's so close, trying to figure out where you're going to qualify, that they have to go down to the thousandths to see the difference between the 2 cars. So it just depends on the application, but they're used all the time, and we're all familiar with them, I would think, because we have all these electronic gadgets and devices. So even if you're not a sports fan, you've encountered these 7-segment displays somewhere. There's 2 types. There's the common anode and the common cathode. And all that means is either they all have the same power source at the top, or they all have the same ground at the bottom. And that's anode to cathode. A diode always flows from anode to cathode. A comes before C. So you either tie them all together at the top or you tie them all together at the bottom. This one is not as popular. It requires an active high. These all require active low. And so there's less anytime you have active low or negative edge trigger, those type of things are used because of their ability to reduce the amount of error that you might encounter. So if you leave all of your inputs high all the time, then you're going to know if something drops out and becomes low. Whereas if it's active high and you're at a low, any noise on that line could possibly push that up into a high. But if you get noise on something that's active low, then it's just you can't get higher. It's already high, and so if you have a little bit of noise on top of that high, it's not going to change the state. And so that's why we prefer to use active low outputs, and why we like to use negative edge triggered flip-flops. The 7447 is one that I want you to know, and I'll probably quiz and test you on this. But it is the decoder. If you remember from 112, our discussion on decoders and encoders and multiplexers and demultiplexers. So the decoder takes something and converts it down, takes a value and then converts it to a single output. Okay. Now you might be thinking to yourself, well, if you're turning on more than one segment, then that's not a single output. And to a degree, you're correct. But you are still turning on a set number. Like if the number is 7, there is only, I guess that would be what? A, B, and C, right? Those are going to come on every single time for the 7. So it is one single output if you count that 13, 12, and 11 are a single output, if they're all high at the same time. Okay, the number 8, if you had 1, 0, 0, 0, then all of them would be on, right? A, B, C, D, E, F, and G. So, that would be a single output. And, if you're going to program something like this, that's how you would program it. You would still program this as a constant. What happens when you have a 0 or a 1? It's just that you write specific outputs when that input is on the terminals here. Okay? So there's a lamp test input to see if, there's a lamp test input, a ripple blanking input and output. And this is the kind of stuff that if you want, you can display a 0 out in front of your number. So let's say that this thing was counting to 100. Okay, it's for a basketball scoreboard. And so sometimes they do score 100 points. Okay. So let's say you don't want to display at least from 0 to 10, you just want the number. So if they make a basket and they score 2 points, then you just want it to show 2. You don't want it to show 0, 2. That's where you would blank out that input, because it can detect. If there's a 0 there, it will blank it out and not display it at all. Okay, so that's an option too. So there's different ways that you can configure this, the way that you see best. If you're going to use the actual chips themselves, and we're not talking about the Altera board, which I'll talk about in a second, but if you're actually physically wiring a 7447 chip up to a 7-segment display, you have to put a network of either 330 or 300 ohm resistors in series. And the reason why is because if you just hook 5 volts to an LED and then ground it, you're going to blow it up because that's too much current. LEDs operate between 10 and 20 milliamps, which means if this is a 5 volt out here, which all digital voltage is all 5 volts if it's high, then that means you have essentially an LED to drive over here with this resistor. And so this, 300 to 330, right in that range gives you about 15 milliamps, right in the middle. So if you just stick with this value, then you should be okay to drive these, and you won't put too much or too little current. Too little current, and it won't even turn on, but too much current, and you'll blow the PN junction of the LED. So it says driving a multiplex display. This is in the next slide. I'm not going to really spend a whole lot of time on this because I just want you to know the operation of the 7-segment display. The 7447 with the 7-segment display. But you can take this even further, and you could, whether this is a, this example is a little bit dated because they're using an 8051, but all we would have to do here really is change this to an Arduino or something, right? Or Raspberry Pi, some kind of a microcontroller. where you can write to certain ports and turn things on and off, and use not only the digital circuitry to do this, but you could write the main part of the program in some type of language like C or C++. So this is an example of something where we're still using digital chips to drive something, and we're also using a microcontroller to run the program. All right, so let's talk about synchronous counters. So we talked about the asynchronous counter, where we can just string as many JK flip-flops as we want together. It doesn't have to be JK. It could be D. It could be a SR flip-flop that's that's wired inside. You could put two of them together and make a JK flip-flop out of them. So we also looked at the different types of IC chips. We talked about the 7490, the 7492, and the 7493. And we're going to talk about a few more IC chips that I want you to know. This particular chapter is one where I do have you commit some of these IC chips to memory because they're used so often in what we're doing here. So the difference between asynchronous and synchronous is that all the clock inputs are tied to a common clock line. Now that's different from asynchronous because with asynchronous, all of the clocks, except for the first one, were based on the Q output of the previous flip-flop. So we talked about the fact that you could get into a situation where you miss a count because you compound your propagation delay, right? It keeps summing together. So if you have 15 flip-flops in series, or if you have them cascading into one another, that's 15 propagation delays. And let's say it's 10 nanoseconds. That's 150 microseconds that you have to deal with. I'm sorry, nanoseconds, right? So that that could potentially miss a count depending on how quick your frequency is. So the difference is now you only have one propagation delay, and so you can run a much faster circuit with just having that one single propagation delay, and you don't have to worry about how many of them you have cascaded together. Okay. So here is a 4-bit synchronous counter, just a mod 16. So this is the synchronous version of a 7493 that can do mod 4. Okay. So again, we're using JK flip-flops, but notice that we're using some of this external circuitry now. Okay, so it's not as simple as just cascading into the next. All of the clock lines are tied together. Notice that only the first one is in toggle mode. Does everybody see this? JK. Right? So these are both tied high. The next JK are based on Q. Okay? And then the next JK is the AND of this Q and this Q. Right? And now this right here will continue on. No matter how many flip-flops you have cascaded together here, you will have this AND gate structure at the top where you're taking the present Q and ANDing it with the previous Q. Or in this case, it's the previous AND gate. Okay? That becomes this top leg the whole way across. If we had 5 of these, we would take this output and this Q and AND them together, and that would become the JK for the next flip-flop. So just follow this formula over and over and over. Okay? That's if you want to use the flip-flops. Now, just like with the asynchronous, okay, we have an IC for that. We have multiple ICs for that, right? And I don't have any good mnemonic devices for these because these screw up the mnemonic devices I have for the asynchronous ICs. So the 74192 is a decade counter. This is like the synchronous version of the 7490. The 74193 is just a binary mod 16 counter. It's kind of like the 7493, so those are kind of similar. The 7492, you can see that they have 2 clock inputs. You can count up or you can count down, which is kind of nice. You just have to activate one of the 2 pins, and you have here some other inputs that you can use to reset your circuit. You have a master reset here. You have a parallel load, so you can start your count at whatever you want and then count down, or you can count up. Just depends on what you want to do. So that's different than doing a master reset. And so parallel load, what that means is these are always tied to either high or low. And when this terminal count gets done, in other words, if it's counting to 15 or 16, when it gets done with that count, it will send a high Well, actually, I mean, this is an active low, so it actually will send a low out here, and that low will get picked up by the parallel load, and this will overwrite the output. It'll parallel load it straight into these queues and bypass all the internal circuitry. So that way you're starting your count at whatever number this is, and let's say it's a countdown, okay? When your terminal countdown is done, comes over here, activates the parallel load, and puts whatever number is in here, and then you count from 8 to 0 or whatever, okay? Or 9 to 0, whatever the count is. So that's one way to do it. The other way to do it would be to count up, and so like you could parallel load a 10 and only count to 16, and so each time it terminates, when you get to the final count, it'll parallel load back in that 10, and then you'll only count 5 before it terminal counts again, and then you'll parallel load. So you can get in a loop this way, you can get a loop this way, or you can switch on and off. Okay, so maybe sometimes you want to count up, maybe sometimes you want to count down. But that's the benefit of having an IC chip like this, is it gives you all of those options, and you don't have to make the wiring changes yourself, right? So it still holds that if you take the output Q, all right, and we look at each output Q out of the flip-flop, okay? If we wanted to create a manual down counter, then we would have to put either have a chip that has a Q not output, or take the Q and run it through a not gate. Okay, if you remember, that's how we do a down counter with the ripple counters. So this way, it allows you to count up or down based on a simple input, and you can also parallel load something in to do a different count, so you don't have to reset it automatically here. So you don't have to use the reset. You could do what I just described. Start your count at a different number and then just continue to terminate to 15 and then load it again and then keep going. Okay, so you have multiple different ways to approach the same problem. So when the max is reached, the function table. So let's go ahead and look at a couple more here. So this is the 74190, which is a BCD counter, and the 74191, which is a 4-bit counter. So this is the same, right, the BCD. And then the 191, so they're a little bit different than the other two in that they have a few different terminals here, and it just operates a little bit differently. So instead of having a specific terminal to count up or to count down, all right, you have one single input, and if it's low, that means that you count up, and if it's high, that means you count down. So you have a single input that controls both of those. Okay, and then you have your clock pulse. So that way you only have one clock pulse in. You still have your parallel load and your terminal count and your outputs. So it's just a little bit different approach. Instead of having, essentially here what they've done is they've combined the up count and the down count. So I guess they have the same number of inputs. It's just that this one can be quickly changed to count up or count down. Okay. So I pretty much described all of this stuff here. The up or down to select up or down counting. They have a parallel load to preset the counter. Terminal count when the max is reached. All right, so the 74160, I really just want you to focus on the 190 and the 191, the 192 and 193. Okay, so those are the only ones that I will test you on. These other ones, I mean, it's just, there's so many different flavors. Here's 2 count enable inputs with a terminal count output. Just depends on what your needs are, and they all do something maybe a little bit different. And so here you don't have a parallel load, you have a parallel enable. Okay, it's just called something a little bit different. So in your book, just like with the asynchronous counters, Kleitz goes through quite a few examples of different types of counters, different frequency division counters. And I'm not going to go through all of these again because, like I said, I'm just going to be reading Kleitz's words, which I don't think translates very well, to a virtual instruction like this, because I can't say any better than he has already said it himself. So here's one that just goes from 0 to 9 and then down 9 to 0 and then back up 0 to 9. So they've got this clever situation here where they've got a clock that's going into the 74190, and the direction, whether it counts up or down, is from this this flip-flop that's in toggle mode, and we have a set over here. So we don't use the reset, but we use the set, okay? So initially, this is like an automatic power-up. Okay, we take this node right here, and we send it through 2 Schmidt triggers to get that nice crisp edge. And it says that it's a low because we know initially this drops all the voltage, and then eventually it's all on the capacitor. So it's low at first and then high. Okay, so it gives it an initial set. So initially it counts down. If we wanted it to start up first, then we would do the opposite. Okay, we would take this and send it to the reset because we would want an initial low. So that's the only change that you would make if you wanted it to start down and then count up. But here we want to count up. So we send the preset signal in here when we power up. It'll count 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. The terminal count will go high. All right, it gets changed into a low with this inverter, and then that low gets accepted on the clock input and toggles this to now it's going to be low, okay? Or, I'm sorry, high. And so when it goes high, then it's going to count down. So then it'll count 9. It'll parallel load this in, right? Because the terminal count made sure that happened, okay? I'm sorry, this got parallel loaded in to begin with, okay? So this is just going to change direction. It's going to stay where it's at, and then it's going to count down, right? The Q output is still at 9 because we have flip-flops in here that didn't just automatically change states. Those Qs are still wherever they were before. So now we just change direction and go opposite. The next example that he works through, and again, I would read these in detail, more so than what I'm trying to describe. But it's the same kind of thing. This one, it says design and sketch the timing waveforms for a divide by 9 frequency divider. So this one, we just want 9 counts. And this one, the 74193, will do 16 total. So we have to have some way to reset it. Here you see that they've just grounded out the reset, okay? And so we're not going to use that at all. What we're doing here is terminal counting at the end of the count. It goes low. That will enable this parallel load terminal, and it will load in 1001, which is 9, okay? And it's in countdown mode because we're using the CPD right here. So it's going to count down from 9 to 0. When 0 gets reached, because we're in the terminal countdown right here, it's going to go low, it's going to parallel load in the 9, and it's going to count down to 0 again. And that process will repeat over and over and over. So here's a situation where we can create essentially what is a ripple counter. It's a divide by n, right? But we're not using the master reset. It's just a different way to approach it. Okay, I think that pretty much takes us through everything that I want to cover for this because the rest of the chapter deals a lot with state machines and VHDL, which we do not cover VHDL in this class. So just to recap, toggle flip-flops can be cascaded end-to-end to form ripple counters, and those ripple counters are our asynchronous counters. And the problem with ripple counters is that they have an accumulation of the propagation delay, and so we can also have a down counter. Instead of taking the Q, we take the not Q as our outputs. Any modulus or divide by n counter can be formed by resetting the basic ripple counter when a specific count is reached, and that's where we used our resets. And it says a glitch is a short duration pulse that may appear on some of the output bits of a counter. So remember, when we create the asynchronous counter, we glitch on whatever mod it is. So if it's a mod 10, we count 0 through 9, and we glitch on 10 to reset the count. 7490, 7492, and 7493 have 4 flip-flops, and there's different configurations that you can make, different connections that you can make to utilize the different halves, if you will, of the IC chip. And so all of them have a divide by 2 section, and then the 7490 has a divide by 5, the 7492 has a divide by 6, and the 7493 has a divide by 8. And you can use one side or the other, or you can combine them together to make a bigger modulus counter. It says 4-bit IC counters can be cascaded end to end. So essentially what you're doing is you're just cascading even more and more flip-flops together to form a higher count than just the mod 16 by itself. All right, and so the example that I used was the digital clock. where we use 7490s and 7492s in different combinations, and you can go back and watch the first video for a little bit of explanation on that. We also talked about 7-segment displays, and they're typically driven with 7447 decoders. And we take BCD data because BCD is 0 through 9, and our digits only go 0 through 9, and so these are appropriate. We take whatever BCD data comes into the 7447, that converts it into a 7-bit code to activate the appropriate segments. And we also talked about synchronous counters, and this eliminates the problem of the accumulated propagation delay. So this allows you to run a much faster clock and a much faster circuit, and you reduce the possibility for error, which is always something we keep in mind in digital circuits and circuits in general. And there's a few more. So these are the 4 that I want you to know for synchronous. 5 if you count the 7447, but that's kind of its own thing. So the 74192, the 74193, 190, and 191. Okay, and so just remember the differences between the 4 of those. And I'm not going to make you remember these. It says the 74160 series goes one step further and allows for truly synchronous high-speed multi-stage counting, which is beyond the scope of this class, but they can do some pretty amazing things. So that concludes Chapter 12. And in the next chapter, we're going to start talking about some different types of counters, not just synchronous or asynchronous, but ring counters and Johnson counters and things like that. So thanks for watching.